Good evening, everybody, and welcome to our presentation about autonomous sailing. I'm Michel Drenthe from Open Web, and this is...
Hello, I'm Ivor Boers, also from Open Web. I'm a Java developer.
And we will talk about our journey in autonomous sailing. Our journey starts in 2017 during Christmas. While we were preparing our own food and we also had some drinks, we were also get into a couple of discussions. And one of the discussions became, we could be the first to finish the Microtransit Challenge. So what is the Microtransit Challenge? The Microtransit Challenge is based on the previous one, where you would, in 1960, would people cross the Atlantic with the Transit Challenge in a one-man sailed boat. They go from North America to Europe. They took about 30, 40 days to get there, and but then later on, in 2005, the microtransit was created. It's created in 2005 by Dr. Mark Neal, and to test out if it would be possible, in 2006 they tested on a small lake in France. They tested out with smaller ships if they could get it autonomous. The test run was successful, and then a year later they tried it again, but then on a more sea-like worthy conditions in the coast of England. But it took until, also that one was successful. Then it took until 2010 before the first participant was going into this challenge. And also there are some rules to the challenge. So you cannot have a boat taller or longer, at least, than 2.4 meters. It can be wind propelled or by an electric motor. And you may not use both. It can be unmanned and it can be autonomous. We are joining the autonomous version, but with the unmanned division, you can go while it is sailing or going ahead. You can send new coordinates towards the boat, and then it changes directions. While with autonomous, it has to do with the public available data or the sensors that are on the boat. There are two routes. There's the northern route that goes from North America to Ireland, and there's the southern route that goes from Europe to the Caribbean. This has to do with the currency of the sea itself. One of the participants inside the challenge is the team Snoopy Snoop, a team joker with the boat Snoopy Sloop. And they have the most experience in this challenge because they have participated about 8 times, where they also participated twice in 1 year. Their longest distance they have made was 850 kilometers, but keep a note aside, after 50 kilometers they were already broken and were going with the tide. In 2018 there were 2 teams that were more successful. On your left, we have the offshore Sansons with sailboil, and this is the unmanned division. So they were able to finish the challenge after 38 days, and they have sailed about 5,000 kilometers. The Sea Lion wasn't that lucky. The purple line is the Sea Lion, and they got into problems, and then it went off the radar, and then they got disqualified because they didn't report back their position for 10 consecutive days. So after 4 months, they found it back on actually quite close to the target they had to. But in Ireland, and as you can see, the boat is missing something. That's quite important when you are a sailing boat, mainly the sails. And it was about 100 nautical miles away from the target it should get. So that is about the Microtransit Challenge itself. So what would we have to do when we are going for sailing itself?
Yeah, so before we continue with our... Does it work?
Yeah.
Okay. Before we continue with our adventure in autonomous sailing, let's have an introduction to sailing itself. I'd like to do some terminology and how sailing actually works and how to control a sailing boat. So let's start off with some terminology, and to do so we'll take a look at it from the top and from the side. Let's start with the top view. As you can see, there's no left and right here. It's port side, starboard side, and the stern. So let's continue to the side. The main part of a boat is called the hull, and the hull is what keeps it afloat. Beneath the water, there's a keel and a rudder, and the keel is there for two purposes, really. It's for keeping the boat upright, and it also has the fin has an aerofoil shape, and it slices through the water, and it makes sure that the boat doesn't drift sideways. And then there's the rudder. It's used for steering, so that's our first point of control for our boat. Now, if we move upwards, we can see there's a mast, and attached to the mast is the boom. The boom actually rotates around the mast. Then attached to it is the mainsail, and we have a second sail called the jib. And that's also our second point of control, is controlling the positions of the sails themselves. They have to be positioned correctly to the relative angle to the wind. So we've seen 2 points of control here. And on a normal boat, it's a winch, which you control the line connected to the sail. And there's a steering wheel for connected to the rudder, used for steering the boat. I want to make a note here, because steering a car works very differently than steering a boat. On a boat, there's a lot of more factors involved, like, for example, the wind direction, wind speed, but also waves, and last but not least, a change in position of the rudder. Now, on our sailing boat, we have 2 servos, one for the winch, which connects to both sails, and one for the rudder. Then there's the sails themselves. Why do they work? Well, they work on the same principles as the wings of an aeroplane. They have a shape which makes it the airflow around it. On the backside, the air moves faster, creating a low pressure area and pulling the boat forward. And that's why it's important to have the correct angle to the wind, so to keep them efficient. Furthermore, there's 2 sails here, and the jib is also very important in reducing the turbulence at the backside of the mainsail, which further increases the efficiency of the mainsail. Okay, so now we've seen how sailing works. Let's get on with our adventure.
Yeah. So our adventure continues in February 2018, where we had our first meeting. And during the first meeting, there were a lot of participants, so we decided to split it up in multiple teams. This made the project go faster, and also to get within 1 year sailing. As you can see, a lot of teams. We also came up with multiple steps to get into getting the boat ready. So we have near our office, we have a lake. We can test run our boat. It's the Loosdrechtse Plassen. And if that one would be eventually successful, we would increase it to the IJsselmeer. And IJsselmeer has a little bit more sea-like conditions, except that the waves are more rapidly and less high. But later on, we would go for more mileage. We would go it from Netherlands to England or England to Netherlands. Depends on where we would put it into the water. Probably from the Netherlands. And as final goal, we would go for the Atlantic itself. We also picked a lot of components at our work. We are doing also IoT at our work. So we have raspberries lying around and groove shields where we can attach sensors to. And we also have a lot of sensors lying around. We picked Python because we are all Java developers, and we went for TensorFlow because we wanted to have some machine learning somewhere. But it's not there yet, but we are prepared. And last but not least, we also need to have a second-hand boat because we need to do some testing. So we set out a plan. It looks quite easy to get there. So let's get next to our first step, getting a boat.
Yeah. we needed a boat, obviously, to go sailing. And we were looking for a boat for testing purposes, not for one that could go immediately onto the ocean. That's why we thought, well, we're probably going to break some things, right? So it would be nice to have some spare parts available, and if it's RC controlled, it would mean we go onto the water sailing. Well, it should also fit into the requirements, of course. And soon we found a class of boats that would fit all our requirements, which was called the K class, and it's actively sailed in the Netherlands. Almost every week there are races on the water. It's actively sailed, which means there's a website which you can order stuff. And there's also a second-hand market for these boats. And soon we found our own model. And it's this one, painted like the fire departments. I still don't know what for. But it means our company colors, like, yeah, it's green and white, so this is different. And it means, yeah, since our Open Web is our main sponsors, so we needed sanding, we needed to repaint it. We in the team, we didn't like the job, so we appointed some volunteer to do the job, to go sand it and repaint it. In the meantime, we took a look at the electronics and we checked all the things that were in there. And it appeared that, well, all the electronics were broken. The battery was really old and it wasn't working anymore. We couldn't find the receiver. So, yeah, we basically had to replace all of it. And also, since we were replacing stuff, we replaced the winch as well. It was an old model. It's been replaced with a new model, which was much more powerful. So we got to know the boat very, very well. But it took a lot of time and cost us a lot of time to go sailing, actually. So, okay, now we have a boat. So let's put some hardware on it.
Yeah. So as I told you at the beginning, we picked a Raspberry for our internal computer. We also needed to have a couple of sensors. We need to be able to control the servers that are on the boat, and we also need to add lights and a communication device to the boat. As the sensors were lying around, these are the sets of sensors we have. I will get into the red part later on. But let's first start off with positioning. We used GPS, of course, for getting its position. It's a serialized version. We get everything as one big sausage in text, and then we have to split it up into the readable messages we need. We actually get around 7 types of messages each second, and we are only interested in one of them. So we discarded a lot of information, but we needed eventually the speed over ground, the course over ground, latitude, longitude, and time and date is convenient for reporting it back to the organization. Next up, we also had the compass, of course, because we need to have the heading of the boat. It's I to C, and it also includes a gyroscope that tells us which rotating axle is currently active when it's on the waves. Next up is also an accelerometer that tells us how much velocity it gains or loses. It has another gyroscope, and the funny fact about this chip, it's also in most used in the Android phones, so it includes a step counter for some reason. So when we turn on the boat and when we start walking with it, we're getting the amount of steps we did it until we put it into the water. Next up, we have an analog sensor that reads out the position of the boom, and you will see behind me the assembly of how we read it. So this is the shaft that's connected to the sensor. There are some gears, and eventually the gear with the hole in it is attached around the main mast, so we can read the angle of the boom. Then we get to the wind sensor, we first tried to create our own wind sensor. We bought an absolute sensor with also I2C. And an absolute sensor has an advantage. When it drops power and comes back up, it still tells you in which position it is currently in. After we attached a vane to it and tried to move it around, we guessed we needed about a hurricane to be able to move the vane on top of it. So we discarded that one and we got this one. It's a nanometer. This works with 4 ultrasonic microphones, or nanometers. And they are carefully positioned, and when the wind blows by, it acts like a microphone, and the one that makes the most noise is the one where the wind is coming from. And the more noise, the harder the wind is. Another reason why we select this one is because it is self-powered. It has a battery inside it. It has Bluetooth Low Energy, which I will come up later on why I mention it especially here. It comes with another accelerometer and a tonometer that tells me the temperature of the sensor itself. And last but not least, it has a developer's manual, which is open source, so we could use it. Next up, we had to decipher the whole thing. So coming back to Bluetooth Low Energy, who have used normal Bluetooth? We're just pairing headphones. It stays paired, and then you are connected. With this one, low energy, you can say you want to connect to it, but you never are paired. This is due to the low energy part. It is instead of you're connecting to it and you keep sending messages, this one sends message back to you. And another advantage is you can attach like 12 devices towards this one and they still get reported because this one is broadcasting. After you are connected to it, your first thing you have to do is to say to it, please enable everything, because when you first time connect to it, it's only giving you the wind and nothing else. And then you have to select within your code first the service and then a characteristic. And the characteristic is shown behind me. It's about 16-bit long hexa value. You have to split it up. You have to swap. That's where the arrows are, because they are lower and higher bits. And that will make up the value and then add some math, and then it will get you the right value. It took some effort to get what. Next up, we have the power width modulator. It's also an I2C. It has at least 16 channels to attach servos to it. We only need 1 or 2 at least. And it has 12-bit of control. And you set up the pulse and the width, and then the servo will move in that direction. Also here we had some challenges because there apparently are a lot of libraries, but the one put in fat in here is the one that works. And as you can see on the movie, we finally got it working. So next up, we have also a whole software around all these sensors.
Yeah, and we won't show you any code, but well, I will take you through the architecture and explain some algorithms. As Michel told you, we have a lot of sensors, and sometimes for multiple sensors for one value. So the first thing to start is the data service. The data service will collect all the information from the sensors, and it will provide a valid set of data for the rest of the system. It's valid data, so it should filter the readings from the sensors. If one sensor fails, then it might take the value from a backup sensor to always have this valid data set, and you can minimize the risk of taking false decisions. So next up is the navigation. This boat has to travel like at least 3,000 kilometers, and it won't go in a straight line directly. We will split up this into multiple segments, and we will do it like this: small geofenced areas. So the boat will travel from point A to point B and stay within the red lines you see here. And when it reaches the circle at the end, then it will continue into the next segment and thus it will travel the ocean, hopefully. So this navigation service will, it will calculate the course which is best to take, and it will provide it to the helm service. Now the helm service is a combination of the winch controller and the rudder controller. The winch controller controls the sails, and it works quite independently from the rest. It just takes a look at the relative angle to the wind, and it will position the sails accordingly. So if the boat steers, then it will automatically change the the angle to the wind, and will change the winch. Now the rudder controller will do its best to keep the course over ground as calculated by the navigation service. There are a few parts here that we like to use machine learning. We're not doing it yet. First, we like to use some standard algorithms. But navigation and also rudder control are things that we can use probably for machine learning. Okay, so let's go sailing.
Yeah. So we're now about June, July in 2018, and we've got the boat working again. The software is working, but keep in mind we didn't put it on autonomous yet. So how does it look like when you're starting to assemble everything? It looks like a pencil box with a raspberry shoved in it, and a matchbox with all the sensor with electronic tape to it, and a power bank beneath it. The wire that sticks out goes to the angle of the boom, and then we had to bring it to the lake. Of course, bringing it to the lake, you also have to set it back up over there. It still was the fire department red here. We checked it, double-checked it, make sure everything is working, and then put it in the lake. So there is some information about this, why we picked the Nederlandse Plassen specific. The Nederlandse Plassen used to be a chemical waste dump for hospital waste. So it's lightly radioactive polluted. And it cost about 200 million euros to clean it up. And that's not what we're going to do. But the advantage is the lake itself doesn't freeze. So we can put it in the water even during winter, and it can still go into circles. At least that's our plan. Next up, after we had making it into the water, you see on the right side the path it took, and someone next to us had a drone and was polite us to provide us with how it actually looks like. It all went well. During halfway the trip, we ran into a problem that we apparently didn't know, that there's a second line inside the boat that keeps tension to the line of the sails. So after when we lost wind and we moved the sails, the rope went beneath the winch, and then the sails got stuck. Luckily, we were able to retrieve the boat back by only using the rudder, so that's the end part that we're getting it back. So, lessons learned, make sure the rope is having all the time tension. So, a couple of weeks later, we put it again into the lake, with this time a different one, and we would go for a duration test. We charged the batteries fully, and we made sure the raspberry battery was also fully charged, and then we went to the lake again and put it into the water. We sailed for more than 8 hours. It was a sunny day, and I don't come that much outside, so you can guess what happened. That's the last line also here. And after we got it back, none of the lights were gone. So we still don't know how long it takes till the batteries are depleted. So this is a small lake. So what will happen when we go thinking big?
Yeah, we're thinking of eventually we'll cross the ocean.
Yeah.
So what happens then, right? We need another boat. What most people think of is high winds, strong waves, and for sure that's what the boat will experience. It will have to be tough enough to survive these conditions. And it's not just the waves and the wind, but also the sun and salty water. It's probably one of the biggest challenges in this micro-transat, surviving these conditions. Another challenge is when there's no wind at all. A boat will need to have some speed through the water to be able to steer. So if our software tries to steer the boat because it's not in a good position, nothing will ever happen. It's probably better to save on energy for when we really need it, right? Plastic soup is another issue. It's reported that a lot of participants, their boats have gotten stuck in fishing nets. And that's just floating around. And for a small boat like ours, this will be a real problem. As you can see here, there's a lot of plastic soup in the oceans. And it can easily get stuck behind the rudder, for example, and our boat will be unable to steer. Then there are some things that's unexpected, like probably a whale popping out of the ocean. If one of these tries to have a look at our boat, probably the boat won't survive, but that's nothing we can prepare for. However, there are things that we can prepare for. There are some known obstacles which we can add to our geofenced areas. Oil platforms, but also islands or riverbanks, stuff like that. We can have the boat move around it. Yes.
Yes, this
Something
one.
like this. Right? According to the rules of the micro-transat, we should follow all the international regulations for ships. And it's stated that a boat should avoid any collision. But how do you do that with a small boat, right? When you have these autonomous cars, they use a LiDAR, right, for mapping the environment, and that's really nice, but it doesn't work really well in moisture environments. It's not really something to use on the ocean. Then there are other things to consider, like radar or sonar or maybe video system, but it uses a lot of energy, and chances of really bumping into something are quite small, I guess. So there's one option that's, I think, is really viable, is the AIS system. The AIS system is something that's required on all bigger ships, and it's transmitting the position, the heading, and the speed of every boat that's on the ocean. And this is a screenshot. There's a website that displays the position of these boats at one point in time. So you can see that it's quite busy on the ocean. So that's something we can use to avoid any collision. So we read the international regulations, and it appears that if you have a boat that's small, then it can be seen as a buoy. And luckily, a buoy doesn't need to have any active obstacle avoidance. So I think we are complying with international regulations as well. It's a small recap.
It's not really following the
Yeah, it's too small for the boats, so it's.
The regulation tells us if there's a passenger or it runs with cargo, then it's a ship. Because we don't have a cargo or a human on board, it's seen as a buoy.
Yes, but I think it's bending the rules a bit.
Maybe.
But that's probably the reason the other participants also called it a buoy.
Yeah. So just to recap, we should design for these rough conditions. You've seen the photo of the Sea Leon. So after a few months in sea, the sail was completely gone. So we really need to have a design that survives these conditions. As I told you, we have to think about energy consumption. and saving energy when possible. So no active, really active, I don't know if AIS counts as active, obstacle avoidance. And we'll just call our boat a buoy, so we comply with all the regulations. Okay, so that's future, but where are we now?
So where are we now with the project? We, as I told you, we have just got the wind sensor. We got it operational and attached into our software. We also got the pulse width modulator. That's the part we are still trying to put into the code because the library doesn't allow us to put it into our software yet, but we are getting there. We are looking into solar panels if we probably going to need a couple of them to regain energy, or as the Sea Lion did, is they calculated how much energy they probably needed and just stuffed the whole boat with batteries. Eventually our project looked more like this. So yeah, the finish line is still there and we're getting there. Especially when our new boat design will probably be ready, but we're first going for the going in circles on the lake autonomously, and we are this close to being there. And that actually includes the end of our presentation. So I hopefully see you all at the drinks, so there are time for questions. Yeah, we have to, according to the rules of the Microtransit Challenge, we have to provide within every 6 hours the position of the boat. So we have to include communication. On the lake nearby our office, we could use the, one of those low energy communication devices just to report it back because they have a lot of range without, but probably when if we look at the other participants, we're going to need to go for GPS satellite communication because that's the only thing that survives the sea, or at least that's available on top of the sea. Yeah. So yeah, we're getting communication, but we are not allowed to put data back into it. It can only tap into public data, so we can tell the boat, go into AES, find all the boats around you, and then avoid them. Yeah?
How do you control the very big waves?
Again?
How do you control the very big wave size?
Make the boat sturdy, and the question is, how do you survive the big waves on the sea? As we have seen in the other designs, you have to make the boat itself sturdy enough, and you are even prepared that it just tilts when it's or gets submerged, and that it should survive that one. So the Sea Boil had a fixed sail that was completely of metal sheets. It looks like metal sheets.
It's like a fixed wing, and
yeah.
We're looking into it as well to have a fixed wing design.
Because that one will survive the wave that doesn't break the mast completely away.
Yeah, as you've seen with the Sea Lion, the hull was completely intact.
Yeah.
And I don't know if things was working well, but it was intact, and only the sails were gone. Of course, this one drifted for months in sea, so that's maybe I don't know what came first. Like.
Doesn't seem that you can buy it off the shelf a boat that can cross the
No, all the participants we have seen so far with creating a boat that's doing the sea have created the whole.
So what's your budget for doing this?
Yeah, we take small steps, but we don't know how much it will cost to actually build a boat that's capable of going to the ocean. We'll take small steps and continue from there. I'm building a small boat and getting some experience with that, and maybe we'll also take steps in that and build bigger boats.
And we have
or maybe we use a standard boat and then convert it.
2.4.
Yeah, 2.4 meters. So there's also a team which uses a surfboard and fitted things on top of that. It's also an option. I mean, I don't think it will survive, but
Most of them didn't.
most didn't. Right.
Why did you choose for sailing instead of electric drive? Because
That one is already done. That one is finished. Someone else did already the electric version. That both unmanned and autonomous is already done. The sailed unmanned version is now also finished. The only one that's left is the sailed autonomously.
And I think it's an extra challenge, so I like the challenge. And I like sailing, so.
And what are your plans after you've reached it? Are you going to use it for drug transport?
Good idea.
We might sell it. No. No, we didn't have plans for what we're going to do for the future with the software. Maybe we just put it on GitHub and then let someone else do the transportation of illegal goods, but not we.
What about if the wind is wrong? Do you have to?
Yeah, we have to tag all the time. So within the navigation, it stays. The area is quite big, so it can stay. It's about 100 meter wide, so it can at least move within the rectangular area. But the helms the boat can argue with itself. So the helms control is eventually the one that will be in control of changing the course of the boat. He gets an advice from the navigation, but he's the one that's going to make the decision. Yes, I'm now going to tag.
Your device to detect the wind is based on microphones, but how does that deal with salty water? It's, well, when the microphone hits salty water,
Yeah.
it's likely to not.
This sensor we bought is who marine tested. It's sealed completely, so there's no way to get water in. And of course, the microphone can get wet, but it is tested that it can be wet because when it is raining on a normal boat and it is a little bit higher, it still gets wet and then it still has the readings. So it's tested that it can survive water.
Yeah,
You also test it by submerging it in water?
Not yet. We had the challenge to get it charged first, because when it arrived, it was completely empty, and it's really water sealed, so there's not even able to connect the cable to it. You have to put it into the sun, and it took about 3 weeks to get it charged. But now it's charged at least all the time, so because it's now standing in the window all the time, and it doesn't get depleted when it's apparently only getting a little bit light.
How do you tackle the problem of when you go with the wind kijken?
Well, we aren't there yet,
Yeah.
but I've seen other teams that have also for this use case. So they have two separate ways of going with, or one program for going with the wind, and one for halfway.
And you were going to use the AIS broadcast from other ships to avoid them, or were you just thinking about it? Because you said we are doing it, so we don't have to actively send out AIS signals. I agree with that.
Yeah.
But it would be very sad if you could not just use the public data.
We are planning to use the question is, can we, if we will go tap into the AES system, if I repeat your question right, and the answer is yes, we are planning that's our way to avoid the other ships at least, so yeah. And the website provides us with an API, and then we say, give us a position, and then it tells the boats around us. Yeah. Oh. Are there more questions?
Okay.
Then I thank you for your time.
Thank you.